Okay, 2D wave interference. This is sort of continued. In a previous video, I talked about what happens when you have a couple of sources generating waves in phase, or coherent waves with the same wavelength and in phase. And we talked about where the antinodal points, or where the points where the waves would be exceptionally large, are. In this video, I'm going to talk about where the nodal points, or the points where there is essentially destructive interference, and so very small to no wave effects. So again, the basic idea here is we have two sources, S1 and S2, and we can think about these sources like drops falling on the top of a lake, and they're making waves which are circular and extending out as concentric circles. So this wave would have been made first and this wave would have been made second, and then these two waves are coming along and meeting at certain locations. And again, in the last video we learned that a point that is equal distance from each source, L1 or L2, L1 2 minus L1 works out to be an integer wavelength, and we just wrote this equation as n minus 1 lambda, so we could start n at 1 instead of starting at 0. If the difference between them is an integer wavelength, that's where we got our antinodal points. So that's not what we're doing in this video. We don't want to do antinodal, we want to do nodal, so let's just get rid of all that. And we'll go over to our nodal ones. So what happens, so there's one, let's say this was another one of our antinodal ones. What happens in this region here that, let's say, is about halfway in between those two things? Here, this wave will travel a distance of L1 to get to this point, and this wave will travel a distance of L2 to get to this point. If it works out that when they arrive at the point, they are directly out of phase with each other, as in at an opposite part of the wave, let's say one's at a crest and one's at a trough or something like that, then those two waves will continue to add in destructive interference, or will cancel each other out when they reach that location. So let's imagine L1 here as a line starting like this. So we'll make him just arbitrary choice here, 1.5 wavelengths. And then let's imagine L2, sorry, that's from the previous video, I'll just get rid of those guys if I can. There they go. Okay, now we can imagine L2. Again, this is this wave starting out from this location, going up and down. And now this isn't really an arbitrary choice. Now I'm choosing it specifically so it'll work out the way that I want it to. If L2 is a little longer than L1, let's say we make it 2 wavelengths, or the key thing here is that these two numbers are different by 0.5, or any amount of that plus an integer value, 1.5, 2.5, so on. Then when this wave comes in, whatever direction it's going, we'll notice that this wave is going the opposite direction. So let's continue these two waves and see what happens. This wave would continue by going down, then up, then down. This wave would continue by going up, then down, then up. We can see here that this half wavelength difference has created a situation where these two waves are opposite to one another. When one is up, the other is down, and when the other is up, that one's down. This creates a situation of destructive interference. That means that these two waves cancel each other out, and that there is very limited waves at this location. It doesn't matter that this was 2 lambda. We could imagine a situation where it was 3 lambda. See, there's 3 lambda. And we see we get the same thing. We continue up, we continue down, and we get the resulting destructive interference. So what's critical here, when I do L2 minus L1, is not the integer that goes on the front. We can add something to it. It's that they're off from each other by a half. So by having them a half a step out of phase, when you continue the waves in either direction, they'll always be opposite to each other. They'll always cancel out. And this integer value here means it could be 0.5, 1.5, 2.5, 3.5. It doesn't really matter. Now, if you imagine then we go back to our pattern, that means that we have these lines. This would be the L1 equals L2. This one would be L2 minus L1 equals lambda. These constructive or antinodal lines. And we also have these spots in the middle. I'll add them in red. And these represent where L2 minus L1 would be equal to half a lambda. And then if we added more constructive lines, what we would see is that we get these patterns where we get a large wave, then a small wave, then a large wave, then a small wave, then a large wave, then a small wave. And so the resulting wave pattern would go big wave, nothing, to another big wave, nothing, big wave, nothing, big wave, nothing. So these antinodal points would be large wave effects. And so if we were dealing with sound, they'd be loud. If we were dealing with light, they would be bright spots. Or if we were dealing with waves, they'd be high to low wave points. Alternatively, these destructive spots down here, which we call nodal points, would be quiet or dark, or the not high or low wave, but the water at normal height. Locations. And that all happens because when the waves get there, they either get there in a way where they line up against each other, or as I showed in the previous video, they get there in a way where they line up together. Just to summarize, then, if we want to know where antinodal points are, or versus nodal points, antinodal would occur when L2 minus L1 is equal to some integer number of wavelengths, as in either they went the same distance to get to the point, or the distance they went was off by some integer repeatable wavelength, so you wouldn't notice that that extra step had been taken. Alternatively, these nodal points would occur anywhere where the waves are half a step out of phase. So something like this, where we continue on down and we continue up, and we see that this half wavelength is the key to making that out of step happen, and we can add in integer wavelengths because they are regularly repeating units. Last but not least, keep in mind our choice of which one was L2 and which one was L1 was arbitrary. So we should say absolute value in this equation, because when we look at our overall pattern, it's the same regardless of whether L2 is the closer one or the further one away. So our choice of which one of these was S1 and which one was S2 was an arbitrary choice. So here we just don't want to have negatives. That is the interference pattern that happens when you have two coherent, that means same frequency and wavelength and same phase waves, interfering. The example I used was like on the top of a surface of water, but also this would work for sound waves or light waves or anything else.